have one question in the box real quick that says, are we going to get the PowerPoint after the session? Absolutely. If you go to my website, sqlballs.com, and I've got a slide at the end of the deck for my resources page, I post all the sessions that I do. After we finish up today, I'm going to put that up online so that way you can get a copy of it. The scripts that I run will also be available as well. Oh, and I skipped that because I didn't talk about it. So first up, we need to talk about heaps versus tables. I've got this nice little Batman versus Predator icon here because the fact is most of the time this is a versus conversation. The reason for that is if you have an Oracle background, the default type of physical structure you're supposed to use in Oracle is a heap. And in SQL Server, the default type of physical structure you're supposed to use is a clustered index. I'm here to tell you that this isn't a versus scenario. Nothing in SQL Server is bad. It's bad when it's not used in an appropriate manner. There are a lot of good reasons to use heaps. There's a lot of good reason to use clustered indexes, but they don't necessarily need to war. It's typically when we switch from one platform to another that we have a preconceived idea of the way that things should work, and that leads us down a particular path. For SQL Server, by default in an OLTP system, we want to use clustered indexes. If we're fast-loading data, we want to use heaps, and we'll talk about that just a little bit more in a moment. First, we need to understand what a heap is. If I take a phone book and I unbind it from its binder, and I got nothing but a bunch of loose pages, and I throw them up all over the air, and they're just scattered across the room, and I say, look at those pages and find Bradley Ball. Well, you don't know if Bradley Ball is in the white pages. You don't know if Bradley Ball is in the yellow pages. You don't know if Bradley Ball has an out up front. You don't know if there's so many Bradley Balls in this phone book that they fall over onto multiple pages of multiple listings. You don't know. So you have to search through every single page, and that's a heap. It is a base table with no physical order. The pages are linked, but they're still just a regular table, and they can be completely out of order in any general direction. Every operation that I do against a heap is a scan because I have to scan the entire object because I have no idea how much data or where the data is located. There's no specific order. And while they do have statistics, that really doesn't help us because if I have to scan something every single time, then there's no way I can use statistics to be able to perform a seek operation. When we look at the physical structure of a heap, the way we break these things down is they have what's called an allocation bitmap, and that is an IAM page, an index allocation map. And what this does is this tracks the physical pages that are associated with indexes or tables. Every individual object will get their own index allocation map. And the key thing to understand is this is what allows us to chain all of our pages together so that way pages can be allocated to different tables, and our IAM pages track specifically what pages go to what table or to what index. So let's talk about some scenarios where heaps are good. They are fantastic for loading staging tables. As a matter of fact, if I have a data warehouse or if I have a bulk load operation that I need to do, what I want to do is I want to take that data, I want to load it into a staging table, and then ETL it out. I can insert a couple million rows into a heap within a couple seconds on a fast enough system to a couple minutes on a moderately fast system. If I throw a clustered index and a couple non-clustered indexes on that same table, that same insert operation could take me over an hour. I had a client that I was once working with, and one of the things we were looking at was how we could load data faster into his environment and into his table. He wasn't truncating and loading the table every single time. He was actually trying to find the incremental data to put in there as part of his loading solution. And I told him what we should do is instead of going into his table where he had a clustered index and 8 non-clustered indexes, we needed a staging table, and then we needed to pull that data out and specifically load it into his clustered index. We were actually able to cut his operation down from about an hour and 15 minutes down to about 23 minutes to load it into the clustered index. Loading it into the staging table itself, which had taken an hour and 15 minutes beforehand, actually took about 30 seconds. The first time it ran that quickly, I had to go through the table and show them that all the results actually made it in there that quickly because it's that much faster. You don't have any overhead. When we talk about indexes and their physical structures in a moment, keep in mind that heaps do not have that additional physical structure, and that's the overhead cost when it comes to bulk inserting something into a clustered index. Most of your temp tables are probably heaps. You can place a clustered index on a heap. You can place non-clustered indexes. You can place a clustered index on a temp table. You can place non-clustered indexes on temp tables as well. But most of the temp tables we create by default are heaps. There's a fast, minimal logging system when you create a temp table in TempDB, or even if you create a table in TempDB, a physical persistent, not even just temp. And most of the time we use temp tables when we're going to slam a lot of data into something very quickly and then pull that data out of there. We use it as a work table, and you want to use your staging tables in the exact same way. Issues that we may have with heaps: poor performance. This is typically when we're trying to perform seek operations, because I can't just get one row. Even if I return one row via my query, I have to scan the entire physical structure. Forwarding pointers caused by updates. So a forwarding pointer occurs when I have a page and one of the columns sitting, or the rows or columns that are sitting on that page, has a column that has variable length data in it, a varchar 500, varchar max, something along those lines. And I go in and I fill up the page, and then I go and I update that variable length field, and it can no longer sit on the page. What happens is we leave behind a 24-byte pointer, and we move that record to a new physical location. That's a forwarding pointer that points out to the forwarded record. And so if I go and I look for that record, I get to that pointer on the page, and it makes me hop forward to find that location. Using sysdmdb index physical stats, I can see what heaps I have that have forwarding pointers. The only way to fix a heap with forwarding pointers in SQL 2005 and SQL 2000 and lower versions was to add a clustered index to it and drop it. In SQL Server 2008 and up, there's actually a rebuild table command, and you can rebuild a heap, which will get rid of your forwarding pointers. Clustered indexes. So your eyes aren't playing tricks on you. That tree is upside down on purpose. And the reason is, when we talk about a clustered index, our leaf is on the bottom. The leaf is level 0, and that's where our actual data resides. You can only have one clustered index on a table, and you have a B tree structure. The leaf is the bottom, we have intermediate levels in the middle, and then we have a root sitting at the very top of our B tree index.